Hi everyone. In this video we are talking about motor eccentricity fault analysis. There are many papers and many projects try to find out the eccentricity fault by observing the electrical characteristics, for example, load diagram or current diagram. Now we will talk about how to model this eccentricity fault in ANSYS Maxwell software. And in the next video, we will talk about how to determine the fault with electrical outputs. First, let's talk about what is eccentricity in the motor. In a healthy motor, here, the right picture, we can see the center of the rotation is equal to the center of the rotor and center of the stator. Here it is a healthy motor. But we have two different kinds of eccentricity. One named static eccentricity and the other one is dynamic eccentricity. In the static eccentricity, the center of the rotation is equal to the center of the rotor. But the center of rotor and the center of the stator are not the same. We have a displacement between the center of rotation and center of the stator. On the other hand, in the dynamic eccentricity, the center of the rotation and center of the stator are the same. But the rotor part are eccentric. It means that the center of the rotor is not matched with the center of rotation. To show these two faults better, I made a video on each one of them. It is an SRM motor with exaggerated air gap. In the low air gap distance, we can't see what's happening there. But in this simulation, we will have a big air gap machine to understand the problem better. In this animation, you can see the static eccentricity. The rotation center is matched with the rotor center and the stator has displacement. Just let's see it one more time. Here it's a dynamic eccentricity. As you can see, the whole rotor is rotating around the air gap. Let's watch it. In the dynamic eccentricity, the air gap is changing by rotating the rotor. It is here, it's a very low air gap distance, here it's a very big air gap. But when the rotor is rotating, the air gap moves around the band. But in a static eccentricity, you can see the air gap is fixed. It's not uniform around the band, but it doesn't change. Now let's go to the ANSYS Maxwell and simulate these two different faults. In the first simulation, we are modeling a healthy motor. Its air gap increased, but it is a healthy motor with a center rotor in the band. In the ANSYS Maxwell simulation, you have to know that the center of the band and center of rotation should be around the z vector. So, to model the static eccentricity, we know that the rotor will be in the center of the rotation band. We have to move all the stator and its winding to get a static eccentricity. Now I will select all the stator parts and all the windings. Now I move all of them, for example, 2 millimeters. Now the center of the rotation is not equal to the center of the band and center of the rotor, but the whole stator moved. In this case, the air gap is fixed. It's not uniform, but fixed, and it's a static eccentricity. Remember that when you are moving the whole objects, you should prevent the intersection between the band and the stator or windings. And if you want to parameterize the eccentricity, you can use a variable instead of a fixed movement. To know more about using variables and Optimetris, you can see my video about how to use variables. Let's go to the dynamic eccentricity. We know that in dynamic eccentricity, the center of the stator and center of the rotation are matched. We just have to move the rotor and shaft, and if there is any winding in the rotor or magnet in the rotor, we have to move the rotor parts within the band. We don't change the center of the stator or center of the rotation. We just select the rotor, shaft, and all the parts of the rotor and move them within the band. For example, 2 millimeters here. Now when the band is rotating, the whole rotor and its parts are rotating, and we have changing air gap around the rotor. Let's see the result of a healthy motor. Here we have a healthy motor. The values are not perfect because we have a very big air gap here, but you can see the torque has uniform values. In the static simulation, here we move the stator, and the band and the rotor have the same center. In this simulation, the produced torque is not uniform. We have some patterns here in the electromagnetic torque. They are not correct and precise results, but you have to notice that we are simulating an exaggerated air gap. And about the dynamic simulation, which is rotor is rotating around the band, movement in different times. If I change the plot time, you can see the rotor position will move and it will have some different air gap pattern. For example here, or the whole rotor and shaft will move in this case. Now let's see the generated torque, and it has another pattern in the produced torque. In the next video, we will see how to analyze the torque, how to analyze the current to find a criteria about diagnosis of these faults. I hope you enjoyed this video. You can follow my channel and write your questions in the comment part. Have a good time.